and other ones that correctly identified those ones, those will be told to basically through backpropagation and gradient descent and calculus, they'll be told to turn on and highlight more. So that's kind of a high level, really simple. This is the sigmoid. This one's a nice function in that it basically centers around 0 and goes to, you know, negative, but it's a nice curve. So basically you can use this one to turn on and off these features. And what these neurons do, they'll end up becoming like kind of specialists. So you'll have a neuron or a collection of neurons that are really good at detecting edges. Some might be like a cat's ear or something like that. So they kind of become really important, knowledgeable, and help with these predictions and whatnot. And how this loss function works is it basically tells these people kind of if they're doing a good job or not. So yeah, this is the loss function at the end. So this is, again, they can kind of be different loss functions, but this is the mean squared error. And so it's basically the predicted value and then the actual ground truth. Jeremy's going to go into it later on, like on unsupervised and supervised learning. This is supervised learning here, and it's basically telling all the collection of the network, all those neurons, how well they're doing in it, and giving them basically a scorecard at the end of the day. And so this is an example, and this is kind of how the actual network learns. And so in green here, that's the forward pass. So this is kind of an arbitrary example with math that makes it a little bit simpler to see kind of how the process works. But on here, you can see that the green is like going through these calculations, and you don't necessarily have to know calculus. At the end of the day, we're going to show some cool things where you don't actually have to know this level of detail, but it is the backwards. So it's basically, again, a reward function and telling all these neurons how well they're doing, how well they're adding contributively. So you can almost think of this as like a circuit. So the beautiful thing about all this is these all kind of have their own individual weights, their own scorecards, and they get told how well they're doing for these different predictions. And so then through backpropagation, it's basically taking the slope of how well they did, and that's the gradient, and showing them how like that neuron's doing a great job of classifying a cat. Maybe it's doing a terrible job of classifying a couch or something like that. So it's turned off for some of those predictions, but turned on these other inputs. And so yeah, this all works through gradient descent. So here's kind of like a topology of like comparing these two parameters, theta 0 and theta 1, and this is basically the loss function. So the red up there, that's, you know, the algorithm's not doing as good. So if it starts off there, it kind of gradually walks down, and you want to move down towards, you know, the deeper blue, where the lowest loss, where it's actually having the best prediction. And so that's kind of how the network learns. It uses, just iterates again and again, and that's why it's helpful to have all these GPUs, because all those GPUs do like minor, really small calculations, but you need to do basically billions of them. And so as you do that, though, it kind of finds the optimal solution globally.
All right, I'll take that. So I have a feeling I might know what you're thinking, which I'll address in a slide from now. But before that, what are the model training strategies? So there's three main categories. There's supervised learning, unsupervised learning, and reinforcement learning. So we're going to focus on supervised learning today, and we're going to do a classification problem. So supervised learning really just means you're going to be learning, or rather training the model with labeled data. So there's a human labeling this data, and that's how the model is going to learn. You can kind of think of it like teaching a kid to fish. With supervised learning, you're going to take the kid to the lake, you're going to cast the line a few times, watch them do it, give them some feedback, tell them how they're doing. Now, supervised learning kind of falls into two different categories. It's classification and regression. So classification is going to be if you're trying to identify what's going on within a finite set of possibilities. So you might have a model that's trying to identify a cat or a dog. That's going to be a classification problem. Regression might be more like you're looking at a data set of housing prices in Denver, and based on different features, you want to predict, you know, what the house price is going to be in some particular zip code. So regression is going to be like a value that's a continuous variable. Classification is going to be some just category, basically. So unsupervised learning, this is when you want to teach the kid to fish, but you take the kid to the lake, you drop them off, you go hit the bar, and by the time you come back, you hope they've learned to catch a fish. It can happen, but it might take a little bit longer. It's going to take some more data. So unsupervised learning is used for a slightly different use case than supervised learning. It is for kind of clustering and pattern recognition with unlabeled data. So you can see the comic down here we've got a human trying to teach a robot what an apple is. And the robot is looking at a picture of the apple. They say, banana? You say, no. They say, is it an apple? You say, yes. Okay, great. So that's good feedback. On the right, we have unsupervised learning, where the robot is really just trying to look at the apples and the bananas and figure out what's different about them. How do I divide them into groups? And it's going to do this without human intervention. So that's the big difference there. And then finally, there's reinforcement learning, which is based on the psychological concept of operant conditioning. So this is when you're trying to influence behavior based on positive and negative reinforcement. So the positive reinforcement would be some sort of reward, and the negative reinforcement would be some sort of punishment or a lesser reward. So this is something that's used pretty commonly in things like self-driving cars. Okay, so back to what you were thinking. What in the world was Ryan talking about with all those crazy equations? Well, it's definitely good to learn all that stuff, but you don't actually have to know all those details to get started with deep learning. Just like learning to program, you probably didn't know how to implement a quick sort right off the bat, but there was a sort function you could learn, and you can still get a lot of stuff done with that. Similarly, with deep learning, you don't have to know all the details right off the bat. Definitely good to learn there, but you can gain that with a little bit more experience. I don't know, has anyone in here taken the Fast AI course? Maybe not? Okay, it's an awesome course. Jeremy Howard is one of the co-founders of Fast AI, and he really believes in the top-down learning process. So the idea with this is, most of our education is kind of based on a bottom-up approach where we learn the fundamentals, and then maybe one day we'll figure out some way to apply it. But, we've all heard the comment, oh, what am I going to do with this math? I don't really know, and maybe you'll find out one day. But with top-down approach, you're going to find out that day what to do with it, and then you can learn the foundational stuff a little bit later. So we're going to go through the rough process of pretty much any supervised learning training. We're going to collect some data, label the data, clean it, and then go through the very important concept of dividing it into training, validation, and test sets. Then we're actually going to train it and then perform some sort of prediction with this model. Hopefully, if Kaggle works on this notebook, we'll find out. So give me just a moment here. Okay, how's the text size? Can y'all see that decently well? Okay. So, has everyone in here seen the show Silicon Valley? Okay, y'all know what I'm talking about, but I'm going to show you anyway. There's probably a few people that haven't. I'm just trying to scroll up right now. Come on. Has anyone not seen Silicon Valley? Okay. Okay. Well, this will be for you.
What are you saying? If I told you there's an apple on the mind, we're past that part. Just demo it. Okay. Let's start with a hot dog.
You'll have to imagine most of the video, but get the audio. He just took a picture of a hot dog and it identified.
I'm going to buy you Lapa of your brain. 12 books rated all these. We'll never hear this words again. I'm going to be brave. On uniform. Two pizza. There's two pizza. Yeah. Pizza.
Not hot dog? That's it? It only does hot dogs?
No, and a not hot dog.
Cool. So for a developer that has never been exposed to machine learning like myself when I first saw it, I was pretty blown away. Like, how would they do that? Stakeholders, they're less impressed, but I thought it was awesome. So Oh yeah, and then another thing that's pretty cool is they actually built a real model to do that for the show, which they definitely did not have to do. So that's kind of what we're going to do today. We're going to create a hot dog or a not hot dog model, and then we are going to go ahead and enhance it to identify pizza as well. And then hopefully that will impress the stakeholders. So let's go ahead and get started. This here is a Jupyter notebook. I don't know if anyone in here has seen this before. I see a few shaking heads, so that's good. This happens to be hosted on Kaggle. You can certainly run it locally if you want. I am going to scroll down. You may have to be patient. Okay. So each of these cells of data, if you're not familiar, they can just run any arbitrary Python code. The first cell, you don't have to worry about too much. It's just making sure I'm connected to the internet. The second one is we're just installing a couple of dependencies, one being FastAI and one being DuckDuckGo search. FastAI is a pretty high-level abstraction on top of PyTorch. It just makes things super, super easy, as you'll find out. So I ran that a minute ago, and it installed. Okay, so the first step of the process is we're going to do some data collection. We're going to go ahead and utilize DuckDuckGo. It doesn't require API keys like Bing or Google or something like that. So first thing is we're just going to go ahead and define a function called search images, and it will use the DuckDuckGo search to perform the search on a particular query that's determined here. We're just going to get 30 images back, which as far as deep learning goes is a tiny amount of data. But surprisingly, it is sufficient, especially for this demo. So if I hit play, it's just going to go ahead and put that function in memory for us. I can't really tell if it ran, but we're going to hope it did. Okay. And then I'm going to scroll down. That is the next step. Okay, so now we have this function in memory. Let's go ahead and execute it. We're just going to try and get a URL for a hot dog photo. So we got one. That's good. Seems that the function is working just fine. Okay, now let's take that URL and actually display an image, make sure it looks as we expect. Okay, you can imagine that's probably a hot dog. There we go. Cool. Okay, so that's working. Now, what we would really like to do is create a hot dog or a not hot dog model. But I just got pictures of hot dogs by typing hot dog into DuckDuckGo. What if I was to type in not hot dog? I'm just going to get pictures back of hot dogs. So that's not going to work very well. So for the sake of this demo, we're just going to go ahead and look for food photos. And that'll kind of be the differentiator. So let's search for one of those and display it. Okay, we got some food back, so that's working. Okay. So this is going to be the next step. What we're going to do now is get 30 pictures of food, 30 pictures of hot dogs, tiny data set. We've got a simple Python loop here. What we're going to do is create a hot dog or not folder, inside of which we'll have two other folders, food and hot dog. For each of those terms, we're going to get the corresponding data and put it in the folder. So why is that worth explaining? By putting it in that folder, we're really labeling the data. So that's the very important part. After that, we're going to go ahead and resize the images. I don't want to go into too many details here, but when we train batches of data in PyTorch, it is going to require that each of our images are the same dimension. There are techniques such as progressive resizing where you can continually resize data as you send it through the model, but those have to be on separate batches, and that's not something we're going to really look at more right now. So I will execute this and start getting our data back. Totally should have hit that play button while I was talking, but lesson learned. Yeah, it's a little spinner here. That just means it's still running. Now it's gone, so we're done. So we have our 60-ish photos. So let's go ahead and get on to the training process. The next thing we want to do after acquiring and labeling our data is clean it. So we're just going to make sure that none of the images we downloaded are invalid. We can do that just simply by running this code right here. Okay, so there was one failed image. We're just going to remove that from our data set. We really don't want to infect our model with that. Okay, we're almost to the really cool part. So we are about to train our model. As I said, Fast AI is an abstraction on top of PyTorch. If you use that, you get a lot of best practices for free. So I'll go ahead and just explain what each of these parameters are. So blocks is basically taking a Python tuple of two items, the input and output. The input is going to be an image block since we're training a computer vision model. And category block is going to be our output since this is a classification problem. We just want to categorize this as hot dog or not hot dog, or hot dog or food in our case. Get image files, not too important. That's basically just retrieving images from the place that we specify. And then splitter is very, very important. We are going to randomly split our data set into two parts. It's going to be the training set and the validation set. And what this is saying right here is 0.2. We're going to take 20% of our data, put that in the validation set. So the big difference between the training set and the validation set is that the training set is what is used to get sent through the training process of the model. The validation set is what is used to validate that it's performing correctly. That's an important practice because models can get into a situation where they essentially just start memorizing the data, where they do very well on your training set. But then if you deploy it out into production, give it some data that it's never seen before, it's not going to perform very well. So that's really the point of the validation set, is we want to make sure our model is going to generalize well enough that it can perform as we expect when it gets data that it hasn't seen before, which is really the entire purpose. Get Y, we're basically just saying, hey, the labels are going to be the name of the folders. And then item TFMS, we're just going to resize each image to 192 by 192, and we're going to use the squish method. So the idea there is that we want, we're probably getting back images that are of different aspect ratios, different resolutions. We just want to squish those images in that case. There's many different strategies there. You can crop images, skew them, et cetera, which are all totally valid, but we'll just squish them for now. So let's go ahead and create this batch. We're not training it quite yet, but this should spit out just some of our labeled data so we can verify that before we start training it. Okay, so you can see here we've got a picture of food, it's labeled food. Hot dog, it's labeled hot dog. That seems pretty good. I'll keep scrolling down. Okay, still looking good. Yeah, I don't see any errors, so our data is in a good spot. So we're getting super close to the training process.
This is really a lot of it. Like 90% of a data engineer or machine learner is just like getting the data just super clean and ready to go. It's just a ton of work.
Okay, so This is kind of the magic down here at the bottom. So we're going to execute this function vision learner, which takes 3 parameters. DLS, this is the object we just defined previously in the cell up above. And then ResNet 18, this is interesting. This is a computer vision model that's pre-trained, provided by FastAI. It is a model that was trained from the ImageNet data set. This is just a collection of millions and millions of images hosted by Stanford. It's called 18 because it's a neural network that's 18 layers deep. There are larger networks, ResNet 50, ResNet 101, but they take longer to train, and it's just, wouldn't make for the most compelling demo in the world. Okay. And then we have learn.finetune. So finetune is a method that is executed specifically for transfer learning. So if we're using a pre-trained model, like ResNet 18 in our case, this is the function we're going to use. It takes parameter 8 in this case, which is the number of epochs. This is basically the number of times we're going to send data. Let me back up. This is the number of times that we're going to look at each piece of data during the training process. Determining what that number should be is kind of a fine art. Really comes down to trial and error at first of all. But based on the output that we can get, this is going to help you determine how to mess with that number. So let's go ahead and run that. So this is another cool thing about Kaggle is we are running this all in the cloud. I can barely scroll down on this machine. I certainly cannot train a vision model. But the fact that it's up there is totally awesome. We've got Kaggle provides free GPUs you can use for training. At first, I was training this with a CPU. Literally this exact code that you're seeing. It took about 6 minutes or so. And then I switched it over to use a GPU, and it's taken just a matter of seconds here. So training is done. We went through 8 epochs as specified up above. And yeah, this is kind of strange. Our error rate is looking concerningly good. I don't know if anything is really going on there, but I did run this earlier with a little bit more realistic numbers. Basically, the idea is the error rate is going to tell you how your validation set is doing against the model as it's getting trained. So you should see that number getting better and better. There are situations where you may see the training loss continue to decrease to a very impressive number, but then your validation loss is going to increase. What that means is you're probably training it a little bit too long. You could have some data problems. You may need to tune some hyperparameters, which we may go into a little bit later. But basically what that's telling you is that your model is starting to memorize your data. It's not generalizing. So let's go ahead and move on forward. We've got a trained model, so let's send some images on through it. Okay, so we still have this learn object. We can just simply call predict on it. We're going to grab one of our previously downloaded hot dog images. This is kind of cheating. You don't really want to test your model with an image that it may have been trained on, but it's good enough for now. Maybe. Well, let's try the other category. We'll tell you what. I'll show you the proof of the pudding. If you all go to this URL I will show you in just a moment, maybe someone can actually test this model out for me. Oh no. So I did deploy this model on Hugging Faces Spaces, that's what they call it. If you're not familiar with Hugging Faces, it's basically like a GitHub of pre-trained models. Okay, I wonder if, can someone go to this URL, or maybe several of you, and just try and plug in a URL of a hot dog or something like that? know what? I suppose I should go there myself. You mind holding this for a second?
You didn't just feed it a roll of a picture?
Yeah, that's right.
Find the picture first,
All right, Control C on Windows. Not used to that. Well, okay, not gonna be able to put that up on here. Adam, Ksenia, Laura, how you doing? Is it working? Okay. So anyway, what I was going to show you is just sending data back to the model, and then going back through the training process, this time adding another category, pizza.
I got it. The winner.
Does it work? So are you lying because you work with me?
No.
Okay.
I just got an error.
I know it works.
I just
Most of
got
the
an
time.
error online. So,
Okay.
Yeah, just an error. I was gonna try it with, there was someone in a hot dog costume, see what it would do with that.
I would be curious about that as well. Yeah, I don't know if you got the
image
URL.
extract- the URL out of it, out of the particular site, but yeah.
Yeah, I did search for some. Oh. Check. Yeah, I did search for some images on Google that just had like these giant URLs, and those were kind of making an error out. Anyway, I deployed that app in like 5 seconds, which is what's cool about Hugging Space Faces, but maybe not the most robust thing in the world. Okay, so anyway, the neural network black box. To quote that same paper that I talked about earlier from Turing, an important feature of a learning machine is that its teacher will often be very largely ignorant of quite what is going on inside, although he may be able to some extent to predict his pupil's behavior. So much like training a human, you know, if I'm hanging out with Laura and Laura is an expert squash player, I don't know if that's true, but let's say it is, and she's trying to teach me to play. She's going to show me some things, give me some examples. She's not going to know what's going on in my head. But at some point, I'm hopefully going to be able to emulate some of the stuff she's showing me. So that's pretty much what he's talking about here.
This one worked.
Nice. Okay, so I'm not totally lying. All right. Oh, yeah, and that's kind of like a common critique of deep learning in general, is that it's this black box you can't quite peer into. That's not entirely true. I've seen examples of a model that was taking pictures of different airplanes and trying to categorize them, you know, 747, 737, and there were some pictures that it was misidentifying. So they took these pictures, and FastAI provides a really cool feature where you can create a heat map on top of these images that kind of show you where the neurons are lighting up on the picture. Basically, at the end of the day, you can see what features the model is identifying and how it's making decisions. So it might show like a picture of a vertical stabilizer, or 2 of 4 wing engines or something like that. And so you could get an idea of what's going on and why they're getting misidentified. So it's not entirely a black box. It's not quite as transparent as a traditional machine learning model where you're doing your own feature engineering. But there's a bit of middle ground there. Okay. So more about transfer learning. Really, the whole reason we were able to create this hot dog pizza model. Oh yeah, you can plug in a picture of pizza, and it should identify that too. Yes, so deep learning models, they're very expensive to train. They require a ton of data. It's just very expensive to acquire and label. But with transfer learning, we had the ability to grab this pre-trained model and just kind of customize it to our needs. We just threw pictures of hot dog, pizza, other kinds of food at it, and we were able to kind of retrain this existing model to do that. It already knows how to identify corners and circles and gradually more specific stuff, maybe planes and stuff for all I know. It's able to categorize 1,000 different categories. So we just added a few more on top of that. Okay, over to Ryan.
Sweet. Do you want to pull up the Stable Diffusion on that? Just yours with Chrome and
Sure.
that, right? I don't want to deal with that laptop. But yeah, so now we're going to show a demo we put together also for Stable Diffusion. So this is something that came out. You might have heard of it. It came out like 30 days ago, but it's an open source text to image generation thing. And it uses a diffusion model. And so as you kind of see here, it starts with a high noise image, and then iteration after iteration, epoch after epoch, it comes up to an actual face. So it's a really, really brand new cutting edge. You might have heard of Dolly, similar kind of thing, but yeah, basically it's state of the art, comes up with cool things. So you got to run in.
We're going to just do a text to image generation here. Does someone want to tell me what to generate?
Yeah, any text prompts? Hot dog. It takes about 15 seconds, like we talked about before. This is running on a GPU on AWS, so it takes a while, or it takes 15 seconds with the GPU. It'd probably take an hour or so with CPU, but yeah, kind of this is like the open source cutting edge of machine learning right now.
Oh, I'm not even online.
That would help too.
Does anyone know the Wi-Fi network?
The ADP guest, and then the password is guest at the, and it's the app symbol. Capital G, yes.
Oh, okay. All right, I'm
Sweet.
online. Let's try that
All
again.
right, let's see hot dogs.
Okay, cross your fingers.
Yeah, the demo hasn't been that smooth, so this probably won't work, but, you know, fingers crossed.
Bam.
Hot dog. All right, how about not hot dog?
No.
You want to try not hot dog?
Elon Musk keep flipping over Jeff Bezos.
Whoa. Now, these models have been specifically designed not to like emulate other humans.
Oh, right. Okay.
But let's try it anyway.
Yeah, we might get a black image. If that happens, it's like censored kind of thing. But it could also be super sweet.
All right, let's see what happens. That's unexpected.
That's pretty bizarre, yeah.
Usually their faces are a lot worse than that.
Yeah, I've actually never seen one that good. It's really
What's
weird. I mean, it's awesome. But,
Wow.
I don't know if anyone listens to Aphex Twin or something, but it's got that creepy face on all of his music videos. All right, give me one more.
A moon over a lake.
So yeah, you'll all be able to hit this too. It's crafted.services. You actually, the back end doesn't have a certificate, so you're gonna have to like allow insecure content on it if you try to use this, but feel free to use it. And it's hackier than that right now, but you can also go to just Stable Diffusion, and I think they'll have it. But yeah, pretty cool photo.
Yeah, I mean, anyone can deploy that for themselves. I have seen a Docker image for us. That's super convenient. Not off the top of my head.
And then this is actually a couple images if you type in Stable Diffusion to Stable Diffusion. So this is like it being meta and introspective right here.
Yeah, so there's a bunch of other deep learning based tools. Really machine learning in general, and then especially deep learning is still in its infancy, and yet it's already made a pretty big impact. So we've got tools like GitHub Copilot. It kind of calls itself the AI pair programmer. Dolly 2, which was the originally produced text-to-image generator from OpenAI. I think it blew everyone's minds. Still, every time I like generate an image, I'm just like, wow, it's pretty cool. And then GPT-3 is, of course, a very advanced natural language processing model. you can go check out a subreddit, I think it's /GPT2, and you can actually see its predecessor having conversations with itself. It's good to know about, a little concerning, super cool. Okay, so the future of machine learning, got to quote Mr. Turing again. We may hope that machines will eventually compete with men in all purely intellectual fields. It could be best to provide the machine with the best sense organs, and what he's talking about here is things like computer vision, like eyes, or ears, for audio processing, and then teach it to understand and speak English. So a little NLP specific here, but still the main point is true. The process could follow the normal teaching of a child. Things would be pointed out and named. So in 1950, Turing already knew that supervised learning was going to be a thing, and was talking about it right here. So the coolest thing about this is that, as you saw earlier with all the equations and things like that from Ryan, there's a lot of researchers doing very advanced stuff that you don't necessarily have to know and understand in detail to make use of. So deep learning is becoming increasingly democratized due to increasing availability of cheap processing power. We can get cloud GPUs, access to massive amounts of data and pre-trained models. So you can really go pretty far. I think a lot of us probably work in various different domains, and most of those have been completely untouched by deep learning. So there's a lot of opportunity out there just waiting to be found. Just want to show a couple Denver-related images. We got Blucifer climbing a mountain and Blucifer at a Denver Broncos game. So. Okay, and then you can check out this URL at some point, which is the exact app we were just showing. So that's just our locally deployed Stable Diffusion. Well, cloud deployed. Anything else from you, Ryan?
Yeah, thanks for the time. Sorry for the slow start and whatnot, but thanks for your patience.
Cool.
Hope you enjoyed it.
Any questions?
What made you guys choose Fast AI and PyTorch over like Keras and TensorFlow?
Yeah, so while taking a Fast AI course, I mean, that's part of the reason is familiarity. But I think one of the reasons Fast AI is built on top of PyTorch is that it seems to be increasing in popularity. It sounds like TensorFlow is a little bit more popular, especially in the research realm. And then PyTorch maybe a little bit more in industry, but even now that's changing. PyTorch seems to be the way things are going moving forward, both in research and in industry. And so just since it's built on top of that, that was the main reason.
They keep getting more abstract, so TensorFlow is pretty nitty gritty. You're down there weaving together networks, where in Keras you can download the in PyTorch, same, like download pre-trained things a lot easier. But
I thought I saw, yes.
So the model that you were using, it was being trained, and it's owned by somebody else, and that intelligence is then shared by people that use it? Or how do you keep when you're training a model for your use, how does that work? Where does that intelligence for that?
Yeah, let me see if I understand your question. So you're saying we were utilizing a pre-trained ResNet 18 model, and you're asking where that came from?
Yeah, like you're adding intelligence to that model. Are you actually leaving that out there for other people to use?
Oh.
Or are you owning that training and intelligence that you've done?
Yeah, I see your point. So the ResNet 18 image is out there for anyone to use. When we train it, we're not affecting that model. So basically, we're making a copy of it and customizing it, and then it's just ours. So, although a lot of people are doing stuff like that and then throwing their models up on Hugging Faces for other people to use and maybe do some transfer learning on. So.
like Stable Diffusion, for example, they spent $600,000 training it, and it took a few 100,000 hours and 256 GPUs on AWS. So not everyone has 600,000, so it's just awesome that they're open sourcing it and making it available.
Yes.
So, but the models that are on all birds in the world, are those all separate models? So is the sum of the size of the files just the weights? After you train the model, is that the size of the model? And so you could have basically one model per bird in the world, or are all the models stacked, or all the birds featured maps stacked into the same model?
Yeah, so there are definitely smaller models, maybe a model that would be dedicated to identifying just birds. You may not find that incorporated with a more general model that's going to be able to identify a chair or shoes or a Buffalo Bills hat. Sorry, can you repeat your question one more time?
I'm just wondering, like, how big are the models, size-wise, like files,
Oh.
like after you trained it, like what are you exporting there?
Yeah, so in my particular case, it was just a pickle file. It was something like 40 megabytes, which is probably influenced by the ResNet 18 model. What I don't know, though, is like, you know, the more advanced the model, does that make it bigger? If it can identify more things, is it larger?
It's just like the weights, right? Because that's what it's like when you're doing on the test data, it's you're passing that through the model, and so you just have, and the weights are changing at that point, right?
Yeah, I don't know the answer to that question, but that seems like that makes sense to me. I would think it's more like the number of layers might influence the file size rather than like the number of things it can identify. But I don't know.
Yeah, it's the
Both
parameters.
dimensions, right?
So
Yeah.
If it's a really like 101 ResNet, it's going to be, you know, literally 101 layers. I don't know how many neurons per layer, but it's a lot. But it's still like bigger models, call it like order of hundreds of megabytes to lower gigabytes.
I just don't understand like how you could fit all the models to identify every bird in the world into like an iPhone app. I mean, it just seems like it would be too big, right?
So you can do like basically, yeah, to Jeremy's point, you can have like very specific models, or you can have like larger that can categorize a million things, or one particular thing, a hot dog or not, or like a dove, right? And so they do have minimization. There's also a trend where like the floating points, like we all started with floating point 64, then it's 32, now it's 16, now they're looking at floating point 8, so you can just like basically fit a lot more data, because the lossiness, like you only need how many significant digits, right, of precision for some of these on the update. Like 64 is obviously way too much, and it's just not as efficient. So like the more you can compress that, the more compute you can do, and then the less storage space it takes.
And I think another thing to keep in mind is like, you know, these Android phones have tensor chips now or whatever that can run these models pretty efficiently. But still, with the more complicated ones, GPT-3 or something, you're not going to run that on any phone. Yeah, exactly. So for the bigger models, you're going to be hitting it running on a remote machine somewhere. Yes.
So if you were to do something different, like you mentioned the recommendation engine,
Yeah.
things like that, versus image categorization, is there a different like workflow process you go through, or is it still like a very similar workflow process for it? Like what are the different, I get supervised versus unsupervised,
Yeah.
but like for the different types of problem sets, are there different types of
Yeah. So it's really kind of totally different on that one. Like it is, that one's like, it's kind of like a similarity matrix on that. So like you'll break it down instead of like pixel data where it's like, you know, values for RGB on particular ones. It'll be like similarities, like, and they're mostly sparse matrices basically at the end of the day. And so like just not a lot of data in there. So yeah, I mean, similar, but like kind of different. I mean, terrible answer, but like it's basically like more binary, I guess, on a recommendation engine. It's like Jeremy really liked this article. Jeremy really liked this movie kind of thing. And then like we kind of have, when you move it towards like a separate kind of space, like Jeremy and I align like a little bit more. And so like then that's kind of the cold start problem. It's like, oh, if like really quickly I like 3 different movies that match up with Jeremy, and Jeremy's seen 1,000 movies, then you basically like call me a Jeremy until you get more data on me kind of thing. So it's a little bit more nuanced, and a little bit more binary, I would say, for that, but yeah.
Yeah, I might
Somewhat
add on to
similar.
that. Like you just saw a little computer vision problem. I had previously done some NLP. The process was pretty similar in that you're still, of course, gathering data, labeling it, cleaning it, training it, you know, collecting statistics, retraining. So it's definitely similar in that kind of way, but it's going to be different tools that you use for that. So, yes.
I think it's similar, but for something like a regression model, which you kind of mentioned, but you still do labeling data.
That's a good question. I haven't actually done regression with deep learning. Have you?
No, I haven't. Yeah, I'm trying to think.
I don't think, sorry, you were asking if you would still label data?
Yeah, and I guess maybe it doesn't apply or it's the wrong thing, but I was sort of thinking of like there's weather models you see a lot now. Like,
Yeah.
what's the weather going to be like? So, you know, it's not a classification problem. It's a regression problem.
Right.
Sure. Yeah, and something like that, it might be done on kind of tabular data, which I think is a little bit less popular with deep learning. That might be more traditional machine learning. But I think I'm kind of speculating here. I think the labels would be like the names of your columns, kind of thing. And you can still, kind of regress over those columns. You may not know exactly what features the network is identifying, but
Yeah, it's where you'd put, I think, more work too on like which important features, like what's more noise and what's more signal, and so like a little bit more like hands-on engineering there.
If you don't want to do any machine learning today, but you have a data stream, are there any best practices in storing that data to where we can build it up over time and then eventually run a machine learning model?
Yeah, absolutely. I mean, I would just say, again, not a great answer, but just as much as possible. Like, you never know really what's going to be the actual signal to it. So the more you can kind of store up and, compress, put it on S3 or Glacier or something and just keep it around, like, kind of the better, because you just don't know what's going to be important. And especially that's even more so, like, the more data you have for unsupervised learning is even more important, because then, like, the computer can kind of go off and find its own patterns versus you guiding it as much.
So just normal data storage, there's no standalone service that would help organize it as it builds up?
No, I would say just, I mean, that's a lot of it, of just the manipulation, getting it all right to fit into the models kind of thing. But yeah, I wouldn't.
I'll do a lot of cleanup later, so. but,
Yeah,
okay.
yeah. Yeah. Yeah, no, that's a great idea. Yeah. Some kind of ingest intelligence there, for sure.
yeah.
Great. Anything else? Yeah.
You mentioned you could have it feed itself.
So that's, yeah, and that's unsupervised learning. And so they'll do that, like, the coolest thing I've seen on that is like they'll put like a lot of sensors in like advanced factories, and then they'll analyze and like vibrations and weird things, and they can kind of predict when parts of the circuit or system are going to fail. And so that's kind of like, we don't necessarily know like intuitively what causes that, but like if you just put like an accelerometer onto a pipe and eventually like the vibration and noise picks up, it can like kind of predict failure rates and stuff like that. Or like I think a lot on hard drives, like especially the old spinning disks, like they can kind of do similar things and predict where these systems are going to fail.
Ted.
Does that mean the transfer learning from the ResNet model protect you from, using like false indicators in the project? So if all of your hot dog images have like a purple background, the model might think the purple background is indicative of a hot dog.
Yeah.
Does transfer learning help you at all there?
Yeah, you're totally right. So if we did that here, for example, I would say it's even probable that it would find that as like a defining feature of a hot dog. And then if I just sent in a picture of a purple square, it'd probably be like, oh, that's a hot dog. You're right, it would do that. And transfer learning by itself is not going to protect you from that. So really, that's kind of one of the big challenges with just machine learning in general is that data cleanup. You want the data to represent as realistic a data set as possible. Hopefully, hot dogs with purple backgrounds is not realistic in your case. Although if it is, I suppose train your model with that. But yeah, the answer is no, it will not protect you from that. Definitely still your responsibility to do the data cleanup, which is one of the hardest parts of the job, probably.
If you have the layers, can you go through like a test replica of multiple different shaders and scalings and rotations to reduce those monochromatic or variations that you're comparing against?
Totally, yeah, and that would be called data augmentation. So yeah, it's like imagine we're trying to identify pictures of teddy bears. And then we get a picture sent into the model that's just like, the one corner of it is the teddy bear. Maybe our model's never seen it, so it's not going to identify it. But you can easily just slice and dice up the images that you're sending in, skew them, flip them, make them black and white, look at just different portions of them. And that's definitely a very effective and smart technique to do, for sure.
Is the ResNet an architected like CNN that they built?
I'm not sure.
I'm 90% sure it is, yeah. Yeah. So it's like they have sandwiches of layers, so there's like a pooling layer, a ReLU layer, yeah, etc. So yeah, I think especially Yeah, no, I think they're convolutionals. I know the trends moved a little bit more transformers. I know a little bit less about them though, but like, yeah, I think you're right.
Are there any privacy concerns with uploading all the data to any of the platforms out there?
Yeah, I mean, I think there's some, like with Stable Diffusion, I think there's some artists that are like, upset that they're like, I think there's one particular artist that has like really cool sci-fi images, and if you actually type that in, there's actually like whole subreddits dedicated towards like the right search terms to generate like really cool images, and some of them's like including like a dolly or an oil painting, or I forget this guy's name, but anyways, there is, I think that's kind of an industry problem of
Is that how the guy won the art contest in Colorado like last month?
I don't know about that. Yeah, sorry.
Me neither.
I think he put in his own terms,
Yeah.
and then just go try and make it big.
But he-
Oh, really?
That was the platform. I didn't know that.
I think it was done.
Okay.
Oh, was it like someone won an
It was
art
a
contest or
contest,
something?
it was like a digital art contest. The assumption was you were gonna build something like,
Oh, nice.
yeah,
Okay.
exactly. And then he just put in the dolly and put some terms in.
It's pretty fun.
Good for him. Great. Well, yeah, thank you all for coming. Thanks for the great questions. Appreciate it.